Hello, statistics and pre-calculus. Welcome to your next video, which is going to introduce you to 6-3 binomial distributions by way of Pascal's Triangle, which is basically a really cool number pattern that actually has some uses in this class. So this is what we know as a blank Pascal's Triangle. This particular example is sort of a triangular assembly with hexagons where we'll put our numbers. You can also see it with squares making up the triangle, or just blank, little like blank spaces where you put in the numbers. But the main thrust is that this is going to end up being a triangular assembly of numbers when we're done. So to get started, the first row here, we're going to put the number 1 in. Now, each consecutive row we fill out by looking at the previous row. So row 2, we're going to fill out by help of row 1. Each individual space where a number goes is the sum of the numbers directly above it. So this space only has one number above it, and it's the number 1. So we also have a 1. Same here. All right, 2 rows down, a lot more to go. So our row 3, we have just one number above it. That is a 1 here. Now this hexagon, we have 2 numbers above it. We have a 1 here, a 1 here. 1 plus 1 is 2. And once again, this is also a 1. So third row, we have 1, 2, 1, something a little different. All right, let's look at row 4. So row 4, our first number, we're going to have a 1 again because there's only one number above it. Our second space will be 1 plus 2, which is 3. Our third space is also going to be, 2 plus 1, which is also 3. And our fourth space is a 1. By now, you should notice our first pattern emerging, which is that the outside numbers on both sides of the triangle are 1, because both on this side and on this side, we're only going to have one number above it, and that number is always going to be 1. So basically all the way down our triangle, which technically goes on forever, we are going to have 1s on the outside. Cool. So that takes up a little bit of work. Now we just have to look at our inner numbers as we go on. So row 5, the second number is going to be 1 plus 3 is 4. Then we have 3 plus 3 is 6. And 3 plus 1 is 4. Alrighty, so that's 1, 2, 3, 4, 5 rows. Let's look at row 6. Again, we'll start with a 1 and end with a 1. The middle is the only thing we are questioning here, right? So just so you guys know, there's an understood 1 there. 1 plus 4 is 5. That's our next number. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And herein emerges our second pattern, which is that the Pascal's triangle is symmetric. So as you can see here, on our even numbered rows, which would be 2 and 4 and 6 and so on, we basically have a pattern that repeats itself backwards, right? So for example, in row 6, we go 1, 5, 10, then we go 10, 5, 1. And so that's symmetric. Basically, if you draw a line down the middle of this triangle, we will have symmetry about that triangle. Now, of course, on our odd numbered rows, like 3 and 5, we have an extra little hexagon in the middle, which doesn't have a partner, so that number will be on its own. For example, we have 1, 4, and 4, 1, but in the middle here is a 6, and same with this 3. So rule number 2 is that Pascal's triangle is symmetric. Now, this is all well and good, and we can keep going down this list if you guys need help going over addition, but this is not a class about addition. This is statistics and pre-calculus. So why does it matter to us? Now, one way that Pascal's triangle is going to help us is in statistics, which we haven't gotten to yet, and we will talk about it when we get there, but just know that this is going to be quite a powerful tool in our statistics lessons. But for now, when we're talking about binomials, it's also going to help us in expanding binomials. So I'm going to show you what I mean. Basically, if I have a binomial, and here I have a very basic one, so no numbers, no nothing, just a and b, and all of that a plus b raised to the 5th power, and I want to expand it. So I could take out the time to say a plus b times a plus b, and then I distribute out the a and the b on both sides, and then I do that 3 or 4 more times. But maybe I'm in a hurry and I don't want to do all of that work. So instead, what I'm going to do is I'm going to use Pascal's triangle to help me do my expansion. So when we are expanding using Pascal's triangle, we take the power of our binomial and then we go down 1 row. So we have a power of 5 here, so we're going to look at the 6th row. And basically the numbers in Pascal's triangle is going to be our coefficients of each of our terms. So we're in the 6th row, so that tells us we're going to have 6 terms. These are going to be the coefficients of our 6 terms. So we'll have a 1, a 5, a 10, and then a 10, a 5, a 1. And then basically we're going to start with a. And we're going to start with 1a, and we're going to have that raised to the 5th. Our next term is going to be a raised to the 4th and b raised to the 1st. And it's all going to be multiplied by 5. So next term is 5a to the 4th, b to the 1st. So our next term, if you're catching on to the pattern, we are going to subtract 1 from the exponent of a. So a is going to be a cubed. We're going to add another to the exponent of b. So b is now going to become squared. And we're going to put the 3rd number here in front of it. So that is going to be 10. Our next one is going to be 10. Oops, I'm still up in my superscript. Plus 10a squared b cubed plus 5ab the 4th plus final one, 1b, Control Shift to the 5th. Of course, we can get rid of these 2 1s because we know that 1 times anything is just going to be that original thing. Here is our expanded form of a plus b to the 5th. So we have 6 terms, like I said. So basically what happens is that we start with our exponent and our a term, and we have a to the 5th times our first coefficient, which is always going to be 1. So we're always going to start with a to the power that we have up here. Then we are going to start subtracting from our a exponent by 1 while adding 1 to our b exponent. And so we have a to the 4th, b to the 1st, a cubed, b squared, a squared, b cubed, a to the 1st. I guess I didn't add that. You guys know. A to the 1st is just a, and b to the 4th. And then finally I end with just b raised to that exponent, and once again, we're always going to have a 1 in front of this term as well. So basically, when we're expanding binomials, we're always going to start with a to the 5th, we're always going to end with b to the 5th, and in the middle here is where Pascal's triangle is going to help us out. So we can also do this with something like an x. So here, x is our a, and 1 is our b. So we're going to start with, we're going to be on the 4th row this time because our exponent is 3. We're going to start with x raised to the 3rd power. Then we're going to add x to the 3rd, x 2 times x to the 2nd power times 1 to the 1st power, which we can just ignore, right? So we'll just have 2x squared, or 2. Why are you guys letting me say 2? It should be 3x squared, right? We're on row 4, so don't mess that up like I just did. Next, we'll have 3 times x to the 1st times 1 squared, which again is just going to be 1, so we don't have to write that, and we don't even have to write that x to the 1st. And then our final term is going to be 1 times 1 to the 3rd, which is the same as just 1. So this is how we would expand x plus 1 cubed using Pascal's triangle. So that's going to make that easier, and again, we'll get into the statistics stuff later, but for now, just know how to vaguely, just know how to fill out Pascal's triangle and how to do really simple binomial expansions using it. Final thing before we go, just a history lesson for those of you who care. Pascal's triangle is named after a French mathematician, but it was not invented by him. It was actually seen in literature long before he had ever even existed. So Pascal lived in the 1600s. This Pascal's Triangle showed up in a Chinese book in AD 1303, and in that book it's mentioned that they had already known about this for 200 years. India, Germany, and Italy all also had references to something akin to Pascal's Triangle before Pascal had even existed. So just remember that history is always written by the people in power, and that's not always who made it up. All right, thanks for coming to my math and a little bit of history lesson, and I will see you next time.